And hello everybody, welcome back to another Gregorius Maths video. Today is day 3 of the Advent calendar, and unexpectedly I had a social interaction today, so I couldn't spend as long thinking about what to make a video on. So today is just a small comment about the relationship between the orbit stabilizer theorem and the first isomorphism theorem. And hopefully tomorrow or someday during this advent calendar, I do want to look a little bit closer at the first isomorphism theorem and launch a small propaganda campaign for the first isomorphism theorem as to why I think it's cool. But anyway, in today's video, we're gonna see how the orbit stabilizer, like the isomorphism that you use in the orbit stabilizer theorem, it gives you the isomorphism that you normally use to prove the first isomorphism theorem. So let's start with the orbit stabilizer theorem. And this time let's state it as, when we're thinking of G mod stab x as now a quotient set, so the stabilizer of x isn't necessarily a normal subgroup of G, it's just a subgroup, but we can still consider the set of left cosets of G by the stabilizer of x. And this is in bijection with the orbit of x. Of course, if you take orders on both sides, then you get sort of the formula for the, by Lagrange, you get the formula for the orbit stabilizer theorem. But maybe this is a slightly more formal statement of the orbit stabilizer theorem, which is that these sets are in bijection. And what do? You take a coset G, a representative of some coset, and you just map it to Gx, like so. And this turns out to be a well-defined bijection, and so these things have the same size, which, okay, I won't prove, but this is the orbit stabilizer theorem. Now, let's apply this. So this action right here could be anything. So let's actually try and get the first isomorphism theorem out of it. So let's consider some group homomorphism phi, or phi, which takes you from G to H. And note that this induces an action of G on H by sending, by the left action, G dot H equals 5, just left, multiplying H on the left by 5G. So this is an action that's induced. And so what I want to look at is the stabilizer of the identity in H. Well, what is the stabilizer of the identity in H? Well, this is equal to the set of all G and G, such that G dotted with the identity of H is equal to the identity of H, which is equal to the set of all G and G, such that, well, this right here, this will just be 5G times by E, but by definition the identity is just doing nothing, so we just get 5G equals to E. But then this is of course equal to the kernel of phi, right? So the stabilizer of the identity coincides perfectly with the kernel, and the image, the spoiler alert, the orbit, well, what is this equal to? This is equal to the set of all, I don't know, let's just say H and H, such that H is equal to, sorry, no, I should, okay, let me just, okay, this is equal to the set of all elements of the form G dot EH, where G is in G. And this is equal to the set of all, Well, again, think about what this does. This is just phi of g times h, but in this case, h is just the identity, so nothing. So this is just the set of all phi of g, where g is in g, and that's by definition just the image of phi. And so, okay, good. Okay, now we're in really suspicious territory. We have the stabilizer is the kernel, the orbit is the image, and the orbit stabilizer theorem tells us that G mod the stabilizer is in bijection with the orbit. But now we get G mod the kernel is in bijection with the image. And that's exactly what the first isomorphism theorem tells us. So indeed, if we just plug this and this into this, then what are we getting? Well, we just get G mod the stabilizer of the identity is in bijection with the orbit of the identity by this via the map which takes the coset represented by some G into G acting on EH. But now let's just replace this with this, this with this, and the appropriate definitions in. So now we just get that instead we get that G mod the kernel of phi is in bijection with the image of phi via the map which sends some representative of a coset of the kernel into, well, G dotted with E of H, again, as we saw here, is just phi of G. And this is precisely the map that you typically see used to prove the first isomorphism theorem. And so in this special case, since the stabilizer in this case is actually a normal subgroup because it's the kernel of a homomorphism, this is a group. This is also a group since in this special case the orbit happens to be a group, and this is a well-defined homomorphism, which you can check, and again, yeah, well-defined. And so this is a bijection by the orbit stabilizer theorem, and you can check it's also a group homomorphism. So indeed, we get more than this. We get that G mod the kernel of phi is isomorphic to the image of phi, which is precisely what the first isomorphism theorem tells us. And so I think it would be a bit misleading to say that the first isomorphism theorem follows from orbit stabilizer, but you can, if you just have orbit stabilizer in your arsenal, in your toolbox, you can, by considering this, arrive exactly at the bijection which you would normally use to prove the first isomorphism theorem. So that's just a nice little nugget of information. And you know, when you look at the orbit stabilizer theorem and you look at the first isomorphism theorem, you think there must be like some similarity here. There must be something going on. And well, yeah, this is sort of what's going on, I guess. This is something that is going on, at least. I don't want to say this is all that's going on, but you know, okay. Anyway, yeah, I plan to make a few more videos, or at least one more video on the first isomorphism theorem at some point in the advent calendar. So hopefully that slightly whet your appetite, where we're going to dive deep into what it's really saying and how it actually just like appears everywhere. But anyway, yeah, I'll see you tomorrow. Good day.